Hi and welcome to a lesson of multivariable calculus. So the previous class we discussed about the limits of functions and we find the limits of the functions, some simple limits and then some limits that does not exist. So we saw that if a limit does not exist, then we need to show that if from 2 or 3 paths we approach and the limits are different on the paths, then we can easily say that the limit does not exist. Simply as we do in the case of a single variable function, that the left hand and right hand limits are not equal, then we say that the limits are not equal, right? But in the case if we need to prove that the limit does exist in case of the multivariable functions, then we need some more knowledge about that, right? So there is a theorem that tells us that in case if the limit exists, how to check that. So the theorem says that if uh, a function of two variable x and y, its distance from some point L is less than or equals to some other function at xy, where the limit for this function at some point AB goes to 0, then we say that then we can write if this is true for all xy values, and the interior of some circle centered a comma b means that in some domain, let's say, then we can say that this limit x comma y to AB f of xy goes to L. So this definition we can use to prove that the limit does exist if it exists, right? So let's take an example and show that the limit, of course, exists for the problem, right? Now here's the problem. We need to prove that the limit exists for this problem. Now one thing, by inspection we can see that this is a rational function, that is x squared y over x squared plus y squared. And if we look at the numerator, the power of the function is 2 plus 1, because the power of x is 2 and y is 1, so 2 plus 1 equals 3. So the combined power of the numerator is 3 and the denominator's power is 2 here and 2 here, right? So these are adding, so the power of the denominator is 2. So since we can see that the power of the numerator is greater than the power of the denominator, so we know that if we say that xy goes to 0, 0, then it seems that this numerator will go will converge faster and faster towards 0, right? And since the power of the denominator is lesser than the numerator, so this will converge slowly towards 0 with respect to the numerator. So this is some intuition for this. Now if we start to prove that the limit exists, and we say that if we apply the same approach as we did in the previous lesson, that we start with 2 paths, let's say x equals 0. If we check this, so we will see that 0 times y over 0 plus y squared, this is 0. And again, if we check with y equals 0, again we are going to get 0, right? Again we are going to get 0. And if we check for y equals to x, again we are going to get 0. Now what's happening here is that we are using multiple paths, and again we are getting the limit 0, right? But it's not sufficient to say that the limit exists by only looking at 3-4 paths or some finite paths, because we need that we know that we can approach a point in space from infinite many paths. Now for this, the definition that we learned just a minute earlier, that if f of x, y minus L, this distance, the value of function at some point a, b, minus this L is less than a function at that point, where this function has the limit that is converging to 0 when applied x comma y goes to AB, then we can say that the limit for this function also exists. That is for f of xy. So now if we suppose that because we are getting 0, 0 from these paths, now we assume that the limit is 0. That is, the function is converging to 0. So we can write that if the limit of this function is 0, so we can say that this mod, this distance should be less than or equal to g of x comma y at the same point, right? At the same point means the limit for this function, that is limit xy goes to 0, 0. So now we can write in this way. So we can write this x squared over y, x squared y over x squared plus y squared minus 0. Now if we simplify, we will get x squared y over x squared plus y squared. All right. Now see that we know that this x squared plus y squared is greater than or equals to x squared for all values of x and y. For all whatever value you put here for x and y, we will see that this relation is satisfied because x is squared and y is squared. So this is positive, this is positive, and when something is added in a positive number, so it means that it becomes larger, right? So here we have only x squared, but here we have y squared as well. So if we add this y squared to this x squared, then we know that this thing here will be always bigger than this one, right? Except if it's both are 0, 0, then we can say that these are equal, right? So therefore, we have condition of greater than and equals to. Now, therefore, I can say that this x squared y over x squared plus y squared is less than x squared y over x squared, because we know that if this is bigger than this thing, then this whole thing is going to be lesser than this thing, because we have removed a value from here, all right? Now there is no y, so and y squared is added to x squared. It means that this denominator is bigger, which implies that the whole function value will be smaller, right? So we can write this thing now. X squared cancels here, and this thing, that is x squared y over x squared, is equals to mod of y. Now if you apply the limit here, that is x comma y goes to 0, 0 to this function, that is mod y, then we will get 0. It means that we get a function g of x comma y. We get a function g of x comma y that we learned in the definition. So what is the function of g of x comma y here? So it is simply mod of y. So that function that we were looking for to show that the limit exists, and the function that is given is less than or equals to this g of xy. And we show that this converges to 0 because this is mod of y, and if we apply the limit 0 comma 0, and we will get 0, right? So this function g of x comma y converges to 0, and this is less than this function. So therefore we can conclude that the limit of this function that is given is exactly 0, right? So the limit is converging to 0. That is, limit is 0. The function is converging towards 0. So this way we can just prove that the limit does exist. So there is, we have to use the definition. It's a complex. It's a complex phenomena. It's not as the case of the non-existence of the limit. It's easier to prove that the limit does not exist, but it's a difficult task to prove that the limit does exist, because one have to find a function such that that function should be greater than the given function, and that also converges to some point, right? So it's a complex phenomena to do that. Now we are going to look at some more examples. Let's suppose we have this function. Now see here that the limit xy goes to 1 comma 0. If we apply the limit here, what we are going to get is 1 minus 1 squared ln 1 over 1 minus 1 squared plus 0 squared, which is indeterminate form. Therefore, now we need to work for something more, right? Because this is not non-conclusive, right? Now let's consider different paths. Okay, so this is 1 comma 0. This point is here on the x-axis. Let's say it's 1 comma 0 here. Now we can approach this point from different paths. We can approach from this path, this line. We can approach from this line, that is x equals to 1. And we can approach from this path like this as well. We can approach in this way as well. So there are multiple there are infinite many paths. We already know that, right? Now if we check with different paths, say x equals to 1, we get the limit 0. Then we check with the path y equals 0, we get the limit 0. And then the third path we check is y equals to x minus 1. All right, but again we get the limit as 0. But we cannot conclude that if we are checking with finite paths and the limits are same, we cannot conclude that the limit exists. But yes, we have some intuition that we can say that this function is converging towards 0 because we can see from different paths that it's just look like that the function is converging. So we can just start with the idea that let's say this function is converging to 0, that is that its limit is 0. So we should get some other function, right, which satisfies this equation. So if the limit for this function is 0, let's say we start and say that this is 0, then we only get this function x minus 1 squared ln x over x minus 1 squared plus y squared. Now again we can say that if we remove this y squared from here, if we remove this y squared from here, what we are going to get is x minus 1 squared ln x over x minus 1 squared plus y squared is obviously less than or equals to x minus 1 squared ln x over x minus 1 squared, right? Because we are removing this y square, and because of this y square present here, the denominator is bigger and the value of the whole function is going to be smaller, right? Therefore, if we remove this y square from here, then this value is going to be lesser than or equals to this one, right? Now here we can see that these cancel out and we are going to left with mod of ln x. So the function g of x comma y we get is mod of ln x. And we know that the limit x comma y goes to 1 comma 0. Therefore, if we apply ln 1, that is going to be 0. Now, since this function is converging to 0, that is g of xy is converging to 0, and this is satisfying this inequality as well, that f of xy minus L is less than equals to g of x comma y, which we show here. Now, this implies that the limit of the function does exist. And it is 0, right? Because we start with the assumption that the limit is 0. So this is the way that we can show that the limit exists, right? So it's something more complicated than the process of showing that the limit doesn't exist. So one thing you should notice here, that this is the mandatory condition that the function you are finding g of xy, that is, which we are showing that is greater than this f of xy minus L, this should converge to 0. This is the mandatory condition. This is you can say that necessary, right? So if this goes, g of x comma y goes to 0, then and only then we can say with surety that this thing, this thing is true. All right. So these are some examples for the existence of the limit. Now for continuity, we have definition that suppose that f of x, y is defined in the interior of a circle centered at the point a, b. That is, it is defining the domain of the function. That let's say the domain of the function is interior of a circle. Interior of a circle means that we can say that it is an open circle. We are not including the boundary. We are just including the interior of the circle, right? So we know that a function is continuous in the interior of a circle centered at point AB. Let's say it's centered here. We say that f is continuous at AB, then we can say that the function is continuous at point AB if the limit is equals to the value of function at that point. That is, the limiting value of the function at that point should be equals to the value of the function at that point. So this is a robust condition that this thing guarantees that the function is continuous, right? So if this function is not continuous at AB, then we call that AB is a point of discontinuity for this function. So this is the definition of the continuity for the multivariable function. It's just an extension of the definition that we learned in case of the single variable calculus. Now let's see here. We are concerned with the continuity of a function. Find all points where the given function is continuous. Now, this is the function. I mean, need to find the points there. The function is continuous, right? Now, notice that it's a rational function, that is x over x squared minus y. So if this thing, that is x squared minus y, is equals to 0, therefore we are going to get the value of this function is as infinity, which we can say that the function is not continuous at that point. So first thing is that this thing should not be equals to 0, right? Because we know that the denominator cannot be 0 for the continuity. So this function is continuous at all points, but not at this point where x squared minus y goes to 0. So therefore, we can say that function is continuous at all points except this point where y is equals to x squared. Okay, now let's see some other example, that is this one, g of x comma y. We have a function g of x comma y, that is x raised to the power 4 over x squared plus y squared. When x comma y is not equal to 0, 0, means where x is not 0 and y is not 0, and 0 if x, y is 0, 0, right? Now, for this thing, we have to, first of all, we have to find the limit, that the limit should exist here. Now, again, by inspection, we can check that the function here is the value of the function is this when xy is not 0, and it's 0 if xy is 0, because we know that if we put 0 comma 0 to the function, we are going to get the indeterminate form, and when we get indeterminate form, so we need to do something more to see that the limit exists or not, right? Now, first of all, we will check whether the limit of this function exists or not. So it's saying that in this part that xy is when xy is 0, 0, the value of the function should be 0. Therefore, we can just check the limit of this function by saying that let's assume that the limit is 0, because if we approach with some multiple paths, we can see that the limit is 0, as we did in the previous two examples. So we need to show that this is less than equals to some function, and we can say that this is less than equals to this function easily, right? Because we are again removing y squared. Now this x squared cancel with some power of the numerator, so we get x squared. That is the function. We can say that, let's say this is h x comma y, h of x comma y equals to x squared. Now if we apply the limit, that is x y goes to 0 0, we are going to get 0. So this x squared is going to 0. It means that this function is continuous. Sorry, the limit of this function exists because in the function we are given that the limit should be 0, and when we check that at x 0 comma 0, we get that the limit is converging to 0 by the definition, right? Because we found a function h of x comma y that is less than this function, greater than this function s, and it's converging to 0. So this function is also converging to 0. Now this is established, right? Now once this thing is established that this is fine, that the function is continuous at the point, now what we need to do, now look here, they have done the same way. We get x squared here, we apply the limit, we get 0 0, which satisfies the function. So we say that the limit x comma y going to 0 comma 0 is in fact 0, right? It's 0. So and the value of the function at x comma 0 comma 0 is also given as 0. Therefore, the value of the limit and the value of the function are equal. That is, it is satisfying the definition of continuity. So x comma y going to 0 0 f is equals to the value of the function at 0 0. So this is what we learned is the definition of continuity. Therefore, we can say that the given function g of x comma y is continuous, right? Let's write g, because in the question the function is given as g. Therefore, the limit x comma y going to 0 comma 0 of the function g is equals to the value of the function at that point, which implies that the function is continuous, right? Going back to the definition, we can just see that this right here, this thing, that is a suppose that f of x y is defined in the interior of a circle centered at this point AB. We say that f is continuous at AB, that is this point at the center point, right? It's continuous at this point if the limit value is equals to the value of the function at that point, right? That just we have shown for this problem, this function, that is g of x comma y. So this is how we show that the existence of limits, and then we can proceed further to show that a function is continuous or not. So hope you guys understand this lesson. In the next class, we are going to start the partial differentiation. Thanks for watching the lesson. This is all for the time being.